One way to think of specificity is, specificity, like in a disease, is the last test or your last hope. Like if you have been marked as positive for a disease, at the end of all your diagnostic and screening tests, let us say that you go to the one test, which will clearly tell you whether you have the disease or not. So that test should be high specificity test. So if you don't have it, it should be able to tell you you don't have it. Right? So that is what specificity is. So in the early stages, let's say that you are looking for cancer, right? Breast cancer in women or prostate cancer in men or some cancer. What do you want to do? The consequences of having it are pretty devastating. So the early test should have very high sensitivity, high recall. Means the slightest hint that you may have cancer, you mark the person for further screening or further testing. And you only screen out people that you're absolutely sure don't have it. So what will happen is you'll end up with a lot of false positives, right? Doubtful cases. Then subsequent tests should be more and more specific. They should weed out the ones who are negative. So specificity is useful for subsequent tests. Sensitivity is useful for the early tests when you can, when you don't mind a reasonable number of false positives. That's one way to look at it. Huh? The next is, what does logistic regression do? Well, it is obviously a process of classification of data with a linear decision boundary. I think most of you got this right. Next was a little bit hard for those of you who don't know calculus, and those of you who have done engineering math with me and so forth, who have practiced basic calculus, would remember that this is fairly straightforward. If you have a logistic regression equation, the derivative of this equation of P in this is actually, you can write it in terms of P or you can write it in terms of X, right? So you wrote it in terms of P, this is correct, but this one is also correct. So this one. So this is in terms of the X, the input features. This is an implicit function of the response itself. And now when we go to neural networks, it is this closed form actually that will be much more useful in backpropagation, we'll see. So this is again kernels. I won't go into kernel methods. Again, a kernel method question, a kernel method question. We'll skip that. This question is, logistic regression is a nonlinear classifier because the logistic function is nonlinear in shape. It is true that the logistic function is nonlinear in shape. However, the decision boundary that logistic regression makes is a linear hyperplane. Right? Hyperplanes are linear. So the correct answer here is false. We'll skip the support vector machine. That was for review. So this problem is something, I sort of told you the story of a quack, right, in the class. Suppose you have a disease that's expressed in 1% of the people. Consider a data set that is sufficiently large random sample of the population. For each person, there are relevant biomedical markers quantified as predictors. So if you want a classifier, then if you want to have a classifier that acts as a basic screening during the regular medical checkup, in order to rule out the possibility of the disease, in the beginning, what do you want, guys? Do you want high false positive, or what can you tolerate? False positive or false negative? Just for early screening, knowing that later on you'll do further screening. For early screening, what is more acceptable?
False positive.
False positive, right? And so you want something that has a very low false negative, very low false negative. A low false negative is that. It is also called a sensitive test or a high recall test. So that was correct. And
so they both mean the same?
They mean the same.
Okay.
So it was a bit of a trick question. I'm deliberately, adding a little bit of a twist to these questions, preparing you for you guys, if you go through job interviews, you'll face these. You should consider a classifier of some value if it has the following properties with respect to the baseline. Obviously, it must beat the baseline. Right? Now, we missed one question, did we? No. Okay. Baseline classifier, what does it do? It ignores all the predictors and just looks for the most frequent, the most common class in the target variable. Right? So if most people are healthy, it will just declare everybody to be healthy. It won't even look at the predictors. So what is the value of the baseline classifier? It sets a baseline, 0R sets a baseline. You need to write a classifier that at least beats the baseline. If it doesn't beat the baseline, your classifier is no use. It's quite useless, actually. Right? So these are kernel questions. I'll skip those. Accuracy is always a trusted metric now. No. Accuracy, people often quote accuracy, that my algorithm or this thing is so accurate. Accuracy does not mean much. For example, if you're looking at a rare disease, any lab test, even the shortest of them, will have high accuracy because most people won't have the disease and it will mark most of them to not have the disease. The question is whether it can identify the true positives, the positive cases as true positive. So that is it. This was just for fun. I thought I'll add this. Cat climbed over the wall. Actually, on my wall, cats keep sitting. And the cow jumped over the moon. It occurred to me yesterday, actually, yesterday evening. Was it yesterday or day before? It was a moonlit night. I had a big moon. In my backyard, when I sit in the evening, I get to see the moon rise every day. Just when the sun is setting on one side, on the other side of my backyard, I'm seeing the moon rise. So you see the moon rise and then you see a cat sitting on the wall. So then this sort of thing came to my mind. Anyway, we won't go over 19. Precision is, what is precision? Precision is exactly that, the proportion of true positive cases in those that were marked positive. So suppose you say that these people have the disease, what proportion of them actually had it? That is the precision. So that is that. Kernel, then this matching is correct. Obviously, true positive specificity is the true positive, true negative over negative. In other words, what proportion of negative cases it could mark as negative. Think of specificity as a robust rejection test. Right? So when you're doing the ultimate test for cancer, before you put somebody through chemotherapy, what is the one test you want to do? You want to do a test with high specificity. Accuracy is that, like how often it is correct. Precision is that, the true positive. How often did it get to the true positive over this false positives? And recall is true positive over positive. In other words, what proportion of the positive cases were actually positive? Specificity is the opposite of recall, guys. That's why a lot of people, they tend to use, medical people, they use sensitivity and specificity because their definitions are so simple. Sensitivity is true positive over positive. Specificity is true negative over negative in that way. Error rate is, of course, the off diagonal in the confusion matrix. False positive and false negative, the proportion of those. What is the F1 score? F1 score actually is just the harmonic mean of precision and recall. So when data is reasonably balanced, or you don't really care that much about overwhelmingly about either precision or recall, one good way of taking an average is to take the harmonic mean rather than the. So what happens to a harmonic mean? You will, if you think a little bit about it, you'll realize that if either precision is too bad or recall is too bad, F1 score will decay. You can convince yourself that it is so. um, by thinking about the harmonic mean. So 1 over F1 is 1 over precision plus 1 over recall. So what happens when, let's say that the recall is very, very low, 1 over recall blows up and it washes away 1 over precision. And because it's very large, then when you compute F1, it just becomes 1 over the bad recall, a bad blown up inverse recall. Right? So, and the same thing is true of the precision. So harmonic mean is the F1 score people value precisely because both precision and recall have to be good for F1 score to be good. You don't always want that. So sometimes in the literature, people will say that we prefer the F1 score because it's a composite score. But you know, situation sometimes demands differently. So use it judiciously. No one metric is the best. Specificity and precision are not synonyms. Logistic regression is a method commonly used to perform nonlinear regressions now. The word regression often trips people. It's a classifier, of course, we know that. And then moving onwards to it, which of the following could be considered an equation for logistic regression? So here, I think most of you got this right. I taught you these two forms, and if you just multiply the numerator and the denominator with e to the this exponential, you'll realize that this is the same as this. So it was nice, Shankar, you got this right. Then to try to capture a nonlinear decision boundary with logistic regression, people often say that you can't do that, right? It's a common thing I hear in interviews, for example. Actually, you can do that by mapping it, expanding it to polynomial basis or using a kernel mapping function. Right? Both of these techniques we did. For example, we could do which data set? If you go and try classifier 3, which is the X-shaped data, you'll realize that if you use polynomial logistic regression in polynomial terms, it will solve the problem. Likewise, of course, a kernel method will solve the problem, right? If you map it to a different space, it will solve the problem. We went over this in the lecture very recently, so I'll skip that. This question is a little tricky, and I don't know how many of you got right. So if you have a disease that expresses itself into only 1% of the population, then a classifier with an accuracy of 99% is good or bad? It is actually useless because it's the baseline classifier. If you mark everybody as healthy, what would be your accuracy? You realize that it would still
99.
Yeah, it would still be 99%. So a 99% accuracy has only maybe a marketing value. It has no scientific value in this situation. So your classifier would be useless. Recall and sensitivity are synonyms. Yes, that is true. And finally, the last question. Sensitivity is the probability of detection of a positive test case. That is what sensitivity is. Like, if you are positive, what is the probability that you will be marked as positive? Right? It is also the true positive rate of the proportion of positive cases. How many did you catch? These are essentially the moment in the frequentialist framework. This probability is literally defined by this statement, the equivalent statements. And that was the quiz, guys. So this was much of this had to deal with this confusing terms like precision, recall, sensitivity, specificity. Much of it dealt with that. And the fact that people often confuse the logistic regression to, they have all sorts of notions. Some people think it's for regression. Some people say that it can only be used for linear classification and so forth. So I thought a quiz to clarify the meaning would be useful. Then F1 score is what we did and some other little things. And that was your quiz for this week, guys.